Now we will start the sixth assignment of the tutorial 4. So, here we are given that ECG signal having a lot of PVCs, okay, that the number of PVCs include the episodes of bigamy. What we mean by that we have alternate cycles, one cycle is big, one cycle is small, okay. And why that is happening? It is happening because of premature ventricular contraction or PVC, which is giving rise to the ectopic beats, okay. So, we are given such a signal with lots of ectopic beats, they are actually PVCs. Now, what we are asked that apply Pan-Tompkins algorithm to detect and segment each bit, okay. So, we get that idea that how Pan-Tompkins algorithm is successful in actually creating those that the QRS complex to detect them and segment those bits, then label each bit as normal or PVC by visual inspection. Once they are actually the bits are labeled, then it is possible to actually suggest that which cycle is normal, which cycle is PVC, and record the number of bits missed, if any, by your detection procedure. Okay. So, if any bit was missed, that also should be noted. Next, compute the RR interval and form factor. Form factor is given as FF for each bit. Okay. Use a duration of 80 samples that corresponds to 400 millisecond spanning QRST portion of each bit to compute that form factor. The P wave need not be considered in this present exercise. Okay. Many times P are not present properly, and because it is ventricular contraction. So, QRS and T, that portion is most appropriate to look for that analysis, and that is why we have taken that portion, that QRS to T, this portion. Okay. Next is compute the mean and the standard deviation of form factor and RR value for the normal bits and PVCs. Evaluate the variation of the two parameters between the two categories of bits. That means that how the mean and the standard deviation varies for the RR interval as well as that form factor for the normal bits and the PVCs. That is what we need to compute. So, let us proceed to get that answer. The first job, like any other assignment, is to collect the data, collect the MATLAB file required to read it, and we need to put the input signal and the MATLAB code in the working directory of MATLAB. Once that is done, we proceed to do the work. First, let us do some brush up. That if we look at the signal, x, then if we take the standard deviation of x, that gives us the activity of the signal. Now, if we take the derivative of the signal x dashed and corresponding standard deviation of that is sigma x dashed, ratio of that gives us the that mobility of the signal. Now, if we take the mobility of the signal and mobility of the that first derivative of the signal and the ratio of them, that gives us the form factor, or in short FF. And now we can simplify that what is mx? It is nothing but sigma x dashed by sigma x. Same way, that mobility of x dashed is sigma x double dashed by sigma x dashed, whereas double dashed is the second derivative and x dashed is the first derivative of the signal x. So, after the simplification, what we find that these two terms they cancel each other, and or no, they are not cancelling each other. So, they are coming here square. So, what we have that sigma double derivative into sigma x divided by the standard deviation of the that derivative of the signal square. That means, we can say the variance of the first derivative of the signal. So, that is the form factor. What is one of the thing we need to compute, and we know that when we are getting the that QRS complex, if this is the first peak R1, this is the second peak R2, this interval is called the RR interval. Okay. These are the two things we are asked to compute in this case. So, first let us apply the Pan-Tompkins algorithm and let us see few cycles of it. Now, if we look at this signal, the first thing what we notice that we have a baseline drift. We see that the way the signal is changing, we have baseline wandering, but our Pan-Tompkins algorithm is successful to get the R waves. Okay. So, first few cycles we could get in this way, and then once we have that the QRS complex detected, and after R we could get actually that Q and S. So, we start the calculation of the form factor. So, here couple of things we have marked that ECG is our ECG signal, Fs is the sampling frequency, T is the time axis, Q1 is the that location of that Q underscore L is the location of the Q, R underscore L is the vector containing the location of R, and S underscore L is providing the location of S points, and all of them we get from the Pan-Tompkins algorithm. Actually, we get the R, and taking that as a reference we find out the location of Q and S, and the corresponding value of at those points we also get, okay, once the location are there. Now, what we are doing that we are going through that length of the that number of cycles we have. If we take any one of them, that Q underscore L, R underscore L, for S underscore L, all of them they have equal number of actually the points, because this is giving us the count that how many times we could get the QRS complex. So, that length essentially is giving that so many times we could find out the cycle. So, in this case that we go through that actually that vector, and we are taking that a part that starting from the Q to 80 samples more after the location of the Q. Now, why 80 samples? Because in this case 80 samples represents 400 milliseconds. That is how we got that number 80, because we are told that we need to take 400 millisecond of QRS and T segment, 400 millisecond of this. Okay. We are asked in the question that 400 millisecond we need to take. Now, once we have that, so this is our signal. So, in the equation what we are talking about, that is x. Next thing we need to find out x dash. Okay. So, we have created that sig underscore d is the first derivative. So, where 1 is giving the variance of 1, that means square of activity, where 2 is giving the variance of the derivative signal, first derivative. So, that is the square of the activity of the derivative. So, that now to form that form factor we need the double derivative. So, we are taking the derivative of the first derivative, and then we are computing the variance of that. Okay. Next, what we are doing? We are computing the mobility of the signal and mobility of the first derivative of the signal, and taking the ratio of the mobility of first derivative of the signal and mobility of the signal to give that form factor of that particular cycle. Okay. So, that is the way, just using the formula we have computed the form factor for each of these cycle. Next is we have to plot it, and we have to show that each of these location that in the ECG signal where is the location of R, where is the location of S, where is the location of Q, and below that we are writing actually below that we are writing that in the text that where is the RR, where is the FF plots are there. Okay. So, we are writing the value of the RR and the FF there. So, let us proceed to see that output which will help us to understand that what we are doing. So, we have the first 10 second of data from the ECG data shown here, and below that we are writing in this line that what is the corresponding RR intervals, and below that we are showing that what is the FF intervals. Okay. So, these are the things we are showing to make it easy to read the plot, and this is the way we go ahead to show that the different periods of the signal. Instead of showing the whole sequence at a time, we are taking them part by part for ease of understanding. Next, we look at that 10 to 20 second. Again, for the ECG, we have marked that the R, then Q, this part, and S, and corresponding that RR values and the F values we have given below. Now, after that we look for the next segment going 20 to 30 second. So, every actually plot we are covering 10 seconds. So, in that way we could show them clearly. Then we go for that the 30 to 40 second. So, in the same way we are showing the location of the R, Q and S, and also the value of RR and FF for each of these QRS complex. Then we are showing it for 40 to 50. So, by that we are actually completing that part, and then we look at that what are the abnormalities in the signal. In fact, each cycle we have that. In this case, we get actually the two kinds of waves are there. First, we would like to draw your attention that we are getting that PVCs. Okay, here one, here another. In between, we get that few cycles which are normal. How do we get that these are PVCs? Simply looking at the height, look at that height is bigger, the width is also bigger. If you look at the width of the QRS complex, that is bigger than the normal. So, that clearly gives us that these actually QRS complexes are abnormal and they are affected by PVC. Now, how do we get that more objectively? So, for that we look at first that RR values, get in the first case it is 144, here it is 158. Compared to that, when we look at the RR interval of the normal cycles, we get it is in between 120 to 126. So, there is some variation in the normal bits also, but RR interval still they are much smaller for the normal bit. Now, let us look at that form factor. For the first cycle of PVC, we get the value is 2.97, almost near 3. Next one is a little bit less, 2.7557. So, what we get, both of them are close to 3. On the other hand, if we look at the normal bits that what we have marked here, it is in between that 1.58 to 1.63. The values are much less. Okay. So, that gives us some idea that how to separate them out. We get the range of the FF values which can help us that to discriminate the normal cycles and the PVC cycles. Okay. So, armed with that information or knowledge, we proceed. What we note first, that higher FF value for PVC. With that, we are taking here a chance that what we have taken, that from the observation we have taken that if we take a threshold at 1.9, above that value, if we have FF, then this should be a PVC bit. Below that value, it should be a normal bit. So, we have using this find command, we get two sets, one is P1 and P2. P1 is giving us all those actually cycles that which are having PVC, and P2 are giving us those cycles which are having the normal cycles. Next, what we do, we can take actually that the RR value for the PVCs. So, using that index P1, we take the corresponding the RR values, we put that in a variable here, and corresponding the form factors also for the PVCs. Same way, we put that RR value of the normal and the FF value of the normal bytes. So, this way what we do, that we get the output, that we get the two sequence separated, and that helps us to do the next few things, that we can compute the mean of the normal RR, mean of the normal FF, standard deviation of the normal RR, standard deviation of the normal FF. Same way, we get the mean of the PVC RR intervals, that the mean of the FF value of the PVC cycles and the corresponding the standard deviations. So, we print them, all of them. Okay. So, that is the next task we have. So, here we get the result that is printed in the screen, that we get the number of normal bits are 275 compared to the number of PVC bits 124. Okay. So, we have more normal bits, almost more than double, and then we look at the mean value of the RR. For the normal bits, it is 117.3, whereas the mean RR value for PVC is 141.5. So, what we get, that the RR interval is much bigger for PVC, and if you look at the corresponding standard deviation, we get for the normal cycles it is 14.78, that standard deviation for the RR of the PVC cycles is 25.24. So, the standard deviation is also increased. Next, we look at the FF value. The FF value for the normal cycle average is 1.67, and the standard deviation is very less, it is in the second order place of the decimal. But for the PVC, the FF value is much higher, it is the mean is 2.81. So, difference is more than 1 of the average value, and though that standard deviation is less, it is in the first order of decimal, it is 0.5. Okay. So, we get that form factor for the PVC is much higher, not only that, the variation is also bigger in this case. So, that is the actually observation we make out of this experiment, and let us collate all the observations what we have. In this case, the form factor is used successfully for the classification of the normal and the PVC bits, and both the mean and the standard deviation of the error interval and form factor, they are greater for the PVC bits than the normal bits. These are the two observations we could make from that exercise. Thank you.